So complement of an event is the probability that of the event not happening. Okay. And then next line, it says since the sum of the probabilities in a sample space, when you add up all of the probabilities in a sample space, it should add up to be 1. If it doesn't, then you either have too many or not enough of the events. You're missing some pieces, or you've got one repeated in some way, shape, or form. So when you add up the probabilities of things happening, flipping a coin, when you add up 1/2 plus 1/2, the probability of landing on heads is 1 out of 2. Probability of landing on tails is 1 out of 2. That adds up to be 1, right? So that's the same thing for any probability situation. The sum of those should be 1 in the sample space. The probability of an event not happening, the notation is this little tilde symbol there before the event name. So that probability is 1 minus the probability of the event actually happening. Right? Again, if I use the flipping a coin idea, if I'm saying what's the probability of this coin not landing on heads, so that would be, the way you would write that would be probability of not heads. Right? Well, that'd be 1 minus the probability of it actually landing on heads. Right? So 1 minus 1/2 is 1/2. We know that it's simple because it's only got 2 options. But when you start adding more options in there, it gets a little bit more difficult in finding the probability of something not happening. Just take the probability of it happening and subtract it from 1, and you get that probability or the complement of that event. All right, so let's look at number 7 there. Get some examples with some actual stuff happening. The probability that it will snow tomorrow is 7 out of 20. I'll take those odds. That's better than what I think it will be actually for a chance of snow tomorrow. What's the probability that it will not snow? So the complement of that. So we would say 1 minus 7 over 20, which would be 20 over 20 minus 7 over 20, 13 out of 20. So the complement, given that the probability of it snowing is 7/20, the probability of it not snowing is 13 out of 20. Okay. Number 8, right across from there, a month of the year is randomly selected. What is the probability that month does not begin with the letter A? Okay, so what's the probability of picking a month that does begin with the letter A? 1/6. How do you get that? 6.
2 out of 12.
2 out of 12. That's exactly right. So we got August and April, right? So that's 2 months that start with A. So the probability of A being the letter is 2 out of 12, and Gavin said that's really 1 out of 6. That's good. So the probability of not picking a month that starts with A would be 1 minus. So the probability of not picking a month that starts with A is 1 minus 1/6, which would be 5 out of 6. Again, this stuff is not just uber complicated at all. It's simple ideas just built into the idea of probability and going about it in a kind of systematic way. All right. Number 9, if a spinner on the left, so this spinner right here, it's got the numbers 1 through 16 on it. You've got it on your paper there. If it's spun, find the probability that it lands on a number that is not prime. Okay, so what are the prime numbers that are on that spinner? Talked about this kind of prime numbers a little bit yesterday. 2, 3, 5, 7, 11, and 13. Those are the prime numbers on that spinner. There's 1, 2, 3, 4, 5, 6 of them. So the probability of it landing on prime is 6 out of 16, which is 3 out of 8, right? So the probability of not prime, 1 minus that, be 5 out of 8. Is that right? Did I count right? 1, 2, 6. I didn't. Yeah, I did count right. So that would be 5 out of 8. Right? I'm sure I didn't miss a prime number. Bam.
How are you getting the top number?
How many prime numbers are there? Like, how am I getting the 5 here? How do you write 1 as something over 8? It's 8 over 8, right? So what's 8 minus 3? That's what I'm getting at. I'm just doing that in my head there. I guess I should write it out. All right. Number 10 says 2 dice are rolled. What's the probability of not getting doubles? Okay, so this goes back to that rolling 2 6-sided die. So anytime we're talking about dice in this class, we're talking about 6-sided dice. So 2 of them are rolled. What's the probability of not getting doubles? So that means 1 1, 2 2, 3 3, 4 4, 6 6. Okay, so when you roll those. So we would need to know how many options. We talked about this Monday. How many, when I roll 2 die, how many different scenarios could I end up with? Maybe it would be good to draw out that sample space. So let's think about the sample space for rolling 2 die. So die number 1, die number 2. So when I roll them, I could get 1 1. I could get 1 2, 1 3, 1 4, 1 5, and 1 6. I could get 2 1, 2 2, 2 3, 2 4, 2 5, 2 6. Or I could get 3 1, 3 2, 3 3, 3 4, 3 5, or 3 6, 4 1, 4 2, 4 3, 4 4, 4 5, 4 6. This might be something handy to have as you're doing some probability stuff. Just have that sample space for rolling 2 die, just because you're going to use it some. It'll be handy to have 2, 5 3, 5 4, 5 5, 6, and then the last one we got 6 6, 6 5, 6 4, 6 3, 6 2, 6 1. Okay. So how many doubles are there? 6 of them. 1 2 3 4 5 6. Right. So that means how many are not doubles? (30 over 36). There's 36 possible ways of rolling 2 die, and so 30 over 36. You're going to reduce that 5 over 6, right? So reduce if possible on that. All right. Compound events. So flipping over to the back side of that. When we talk about compound events, there's 2 different kinds of compound events. There's independent events and there's dependent events. Okay, so independent events, the outcome of one event is not going to affect the other event. Okay, so when we do that, the probability is an and situation. Okay, and to find the probability of an and situation, you multiply the 2 probabilities together. An example of 2 independent events would be just like taking 1 rolling die and rolling it, recording what you got, picking it back up and shaking it around and rolling it again. What happened on the first roll does not affect what happened on the second roll. Same way with if you're just guessing on a multiple choice question, if you guess on the first question, whether you get the first one right or not, if you just guess on the second one, it's not affected by what you made on the first one. Right? So independent events, what happens first does not affect what happens second. And the probability is found by multiplying those two individual probabilities together. Okay. Now, the probability of dependent events, that's when things are affected. And a great example of dependent events is a deck of cards. Drawing one card from a deck. If I draw one card from a deck, I'm looking for probability of drawing a heart. That's 13 out of 52, right? 13 hearts. So I have a probability of drawing a heart by 13 out of 52, 1 out of 4. Okay. If I put that back, it's independent. If I put that back into the deck and reshuffle, it's an independent event. But if I take that card out and I draw it, and then I lay it over here to the side, and then I go back to the deck and draw another one, that second time, that makes it a dependent event. So when you, with replacement is independent, without replacement is dependent. That's the kind of the idea you want to get in your head here. With replacement is independent, without replacement is dependent. Okay. So to find that probability, the probability of event A times the probability of event B after A occurred. And that's like, if you don't put the card back, it changes how many you got to choose from, right? So instead of probability of drawing another heart is out of 51 for the second time around if I don't put the first one back. Okay, so that's what changes there. Okay. So this is with replacement. I'll write this somewhere on your paper. And the dependent events is without replacement. Those are the key words some of the key words that you want to look for, or the key concept in a problem. They might not say the word with replacement exactly, or they may not say the words without replacement. They'll say lay that aside, or something like that. So know the independent events with replacement, dependent events, you're not putting it back. Okay. So let's look at the problem, the examples that go kind of with this. A die is rolled 3 times. What's the probability of getting ones on each roll? When I roll a rolling die the first time and I get a 1, can I take that 1 out off the roll? No, I can't. Right? So this is going to be an independent or dependent event. Independent. We're rolling it 3 times. What's the probability of getting a 1 the first time we roll? 1/6. What's the probability of getting a 1 the second time we roll? 1/6. And the third time? 1/6. We multiply all those together. 1 times 1 times 1 is 1. 6 times 6 is 36 times 6, 216. Or Ted talked about this on Monday, when another way of writing that would be 1/6 to the third power. That's the same thing out of that. Okay. All right. Number 12, a coin is tossed, then a day of the week is selected. What is the probability of getting tails, then the day starting with the letter T? Okay. A coin is tossed, then a day of the week is selected. Is that independent or dependent? Independent. Tossing the coin doesn't affect the days of the week, right? We're not taking anything away from that. So what's the probability of getting tails when we toss the coin? 1 out of 2. How many days of the week start with T? 2. How many are in a week? 7. Good job. All right. So multiply those together. Just simple fraction stuff here. The 2's cancel and get 1 out of 7. The probability of that combination happening. All right. Here's a classic example. You've got a bag. It contains 8 red crayons, 14 purple crayons, 6 yellow crayons, and 4 green crayons. A crayon is selected, replaced, then another one is selected. Find each probability. So reading that, it says it's replaced. So is this independent or dependent? Independent. Okay, so every one of these, 13 through 16, is independent because it said it was replaced. Okay, so probability of drawing a purple crayon, probability of purple, then yellow. So what's the probability of drawing a purple? 14 out of 32. Where did 32 come from? Adding up all the crayons. So 8 plus 14 plus 6 plus 4 is 32. So 14 out of 32. What's the probability after we put that purple crayon back? What's the probability of drawing a yellow crayon? 6 out of 32. So it's independent. So we're just going to multiply those two probabilities together. I'm going to simplify a little bit as I go here. 2 goes into that 7 times, and into that 16 times. 6 divisible by 2. 7 times 3 is 21, and 16 times 16 is 256. Purple then yellow, 21 out of 56. Number 14 right there across from it, green then red. What's the probability of green? 4 out of 32. 4 out of 32, not 8. And then probability of red, 8 out of 32. Cross cancel a little bit there. One out of 32. Probability of green and red. Okay, 2 purples. Probability purple, 14 out of 32. We put it back, same probability again. Reduce there. 7 over 16 for both of them. And that'd be 49 over 256. Probability of 2 yellows. What are the 2 probabilities we multiply together? Thank you. 6 out of 32, 6 out of 32. We'll simplify. 3, 16, 3, 16. It's going to be 9 out of 256. Not too good a probability of picking 2 yellow. Really, none of those are really good chances. But all right. Got a label there on that. It says this next ones are dependent events. Why are they dependent? Not replaced. The word not replaced are in the instructions there. So using the same example above. So the same sample set with the bag with the crayons. So we didn't have to read. We got that. Okay. So we still got 32 crayons. We still got the same number of yellows, reds, purples, and greens. Okay. So probability of a yellow and then getting a red. So what changes for that? So probability of a yellow was how much? 3 over 16 or 6 out of 32. I like to use the unreduced first. Then we're multiplying times the probability of getting a red after we picked one yellow. So if we picked one yellow out, how many crayons are in the bag now? 31. So however, how many reds there are, There's only 31 crayons in there. How many reds were there? How many? 8. So it's 8 out of 31 there for the probability of a red after we pulled the yellow out and didn't put it back. Okay, reduce. That'd be 3, 16, 1, 2. So 3 out of 62. Possibility of that happening. Probability of that happening.
How did you get that down to 32?
Like this. I reduced the 6 and the 32 by 2, so I got 3 over 16, which is what Shaw said was the beginning. And then I reduced with the 8 and the 16 to change that to a 2 out of that. It really doesn't matter if you cross cancel. If you just want to multiply straight across and then reduce it, that's fine too. It works the same way. You should end up with the same answer as far as that goes. All right, 18, purple, then green. Probability of purple. 14 out of 32. If we take that purple out, there are now how many crayons in the bag? 31. And how many green ones do we have to choose from? 4. And then simplify if you can. I'm going to use the 4 into 32, and then 2 into 14, and 2 into 8, and get 7 over 124 out of that. $19, same situation, probability of 2 reds without replacement. So what's probability of getting a red? 8 out of 32. If we get a red, how many reds are left? Out of 31. So simplify if you can. 7 out of 4 times 31 was 124. Did y'all ever go to like the Harvest Festival at the elementary school? When I was a kid, they always had the hay bale game. They had the pencil stuck in it. You had some of them were sharpened and some weren't. And I can't remember. I hadn't done that in a long time. I think it was you had to pull 2 sharpened ones out, and you won a prize if you pulled 2 sharpened ones in a row. And now I think back at that, and there were like only 4 or 5 sharpened ones on that day on a whole bunch of pencils. You had to pull 2 sharpened ones out of it. The probability of pulling a sharpened one and then handing that to the person running the game and then going back and pulling another one wasn't very high. But it seemed like everybody won. I don't know. Maybe there were more sharpened ones in the mail than I thought. Out of that. So when you grow up, the things that were simple and fun are not simple and fun anymore. You start thinking about them in different ways. So I think about them in that way now, which is depressing probably, but maybe you'll think about this when you see that game later on in life. All right, probability 2 greens. How many greens are there? 4 out of 32. If we get a green, there are now 3 out of them. 31. So 1/8. So that'd be 3 out of 2 times 124, the 248. Not a good chance, 2 greens. All right. 21. Different situation. We're dropping the idea of the crayons in the bag. We're going to a card. Card drawn from a standard deck. Remember we talked about that Monday, what a standard deck has in it, and not replaced. And then another card is drawn. What's the probability of choosing a heart, then a spade? Okay. So what's the probability on the first draw of picking a heart? 13 out of 52. We pull that out. Let's say we got a heart and we laid it over to the side and we didn't put it back. What's the probability of picking a spade? 13 over 51. Cross cancel if you can. This will reduce to 1/4. And then we get 13 over 204. Not too good a chance there. It's what makes blackjack pretty tough, because you got to draw certain cards to get a certain number for your cards to add up to. It makes it a little difficult. Doesn't necessarily matter what suit it is, but it's pretty tough to, or the probabilities are not good for that. So the house wins most of the time. Keep that in mind if you ever start gambling. 22. Jack had 4 Snicker bars and 8 Mars bars. He randomly chose a piece of candy and ate it. And then he chose another. What's the probability that both candy bars were Snickers bars? Okay. What's the probability of picking a Snickers the first time? 4 over 12. And if we ate a Snickers, there are only 3 left, right? How many were in that bucket or bag or whatever? They're not 12 anymore. 11. We done ate one. So cut it down there. So 1/3. And then that simplifies a little bit more. So 1 in 11 probability of eating 2 Snickers in a row. That's a probability of me eating 2 Snickers in a row is probably a little higher than that. I'm probably not going to. If I pulled out a Mars bar, I'd probably put it back and get a Snickers bar because they're better. All right. So independent and dependent events. All right. All right, guys.